Okay, in this video I'm going to do the same problem, that is problem number 12, using strictly calculus. Now, a couple of things that I want to bring over that I don't want to have to do over again is to say that 45 miles per hour is equivalent to 66 feet per second, 30 miles per hour is equivalent to 44 feet per second. All of that we'd still have to do again. And using this simple diagram, I think it's still helpful here. Of course, once you see the diagram, then figuring this out all using geometrical formulas would probably be much easier. But it could be given to us in a way that it was an irregular curve and we couldn't do geometric formulas and would have to do this using calculus, using integration. So that's what I want to go through at this point. Right, the first thing I'm going to state is that we're given a constant deceleration, so therefore I'm going to let the a of t, the function acceleration function, be equal to the constant k, and that's an arbitrary constant. Alright, now since we have acceleration, we can take we can find the velocity function by taking the integral of that. So velocity is the integral of a of t dt, which is just the integral of k dt, and that is kt plus c. Now, we have this unknown constant of integration, but actually, if we knew the velocity at one point, we could plug in that value, and we could actually solve for c. Well, we do know the velocity at one point. We know that at time t equals 0, the velocity is 66. So k times 0 plus c equals 66, and that means that c has to equal 66. And therefore, v of t is equal to kt plus 66. And so from the basic constant deceleration and knowing the velocity at a point in time, that is at t equals 0, the velocity is 66, we can then find a formula for velocity in terms of k. And we have it there. Now, knowing velocity, we could do the same thing with position. And why would we want to do this? Well, we're given a position, a change in position of 264 feet, and we're trying to find another change in position. So it seems logical that we'll need the position function in here. And that position function then is just the integral of kt plus 66 dt, which is going to give us kt squared over 2 plus 66t plus c. Again, if we knew the position at a particular point in time, then we could also solve for that constant c. And what we're going to assume here is that we're not really concerned about position in this problem so much as we're concerned about change in position. So we're never asked and we're never told where the car is at any particular point in time. We're only told how much distance has been traveled over a period of time. So we're going to assume for purposes of this problem that at time t equals 0, the position is 0. So S of 0 is, going back to that previous formula, it should be kt squared over 2 plus 66t plus c. So I've added that in there. And since plugging in time t equals 0 into that function should equal 0, therefore c has to equal 0. And we get that the position function is 1/2 kt squared plus 66t. And we have two formulas now. Now, how do we go on to use this information? Well, we do know that by the fundamental theorem that the integral from 0 to a of t dt is really just the antiderivative of a evaluated at the upper limit minus the antiderivative evaluated at the lower limit, which is v of a minus v of 0. So v of a is ak plus 66. v of 0 is 0 times k plus 66, and that leaves ak. But we're also told that v of a is equal to 44 and v of 0 is equal to 66. And so 44 minus 66 is equal to negative 22. And so therefore k is equal to negative 22 over a. Now we're going to see why we'll use this in a moment.